Started here. Today I'll be talking about battery design and development using a digital twin. And my name is John Wilson, as Lynn said. I'm based out of Houston, Texas, and I'm a technical solution consultant with Siemens in the 3D Fluids and Thermal Center of Excellence. And today I'm giving this webinar in collaboration with our partner, Sean Sullivan, who's a VP within the design pillar at Engineering Industries Excellence. So as I begin, I'll go ahead and just turn off my camera so that you can focus purely on the slide deck here. But you should still be able to hear my voice, of course. I just want to give a little overview of lithium-ion batteries in general. I'm sure those of you who are attending this, most of you are quite familiar, but there may be a couple who aren't. So essentially, right here, these are the traditional components of a lithium-ion battery. You have an anode with the collector right here in the orange. The anode has an active material, in this case, graphite, which is lithiated. So it contains lithium. Then you have the porous separator, which is permeable only to lithium ions, so not electrons. And then you have the cathode, in this case, lithium metal oxide. And within the active material, and it's also porous, and within the active material of both the anode and the cathode, you have an electrolyte. And then, of course, you have the cathode current collector. Essentially what happens during discharge, you hook up your load, and that causes the lithium to dissociate into a lithium ion, which is transferred through the porous separator into the cathode active material, where it intercalates. And then an electron from the dissociation is transferred up here through the current collector into the load, and then back through into the cathode current collector to reform with the lithium ion. This is essentially the discharge process. Charging is basically the opposite of this. There are a lot of places where lithium ion battery technology is used today. Electric vehicles, electric toothbrush, your cell phone. Also, these UAVs, these unmanned aerial vehicles that are being developed right now. You can see that it has many different propellers here, and that it's also being powered by, in this case, a lithium-ion battery most of the time. So what are factors when you're designing these battery cells? What are important things to consider in battery development? Well, you want high power for fast charge, high capacity, lots of energy, longevity. You want the battery to last a while. And then safety is, of course, very important. The size, the weight, the cost. You'll be really conscious of weight if you're designing one of these aerial vehicles right here. So that's something to consider. And then you want it to be less sensitive to environmental conditions. So, you want the battery to behave well, both in, for example, Canada during the peak of wintertime versus, South Texas during the peak of summer. And so you also want strength of the battery and a protective casing potentially. And a lot of these factors can be competing. So they say that there's no free lunch in battery design. Cell design optimization, while critical, is challenging, and cell design is indeed a delicate balancing act that involves a large parameter space. As seen on the left-hand side of the slide, battery requirements often work in opposition to each other. Selecting battery materials with high energy density, such as high nickel NMC cathodes, often comes at the expense of reduced battery safety. And designing a battery cell for fast charge capability, for example, by reducing the electrode layer thickness, often comes at the expense of reduced energy density. Therefore, it is critical to make design decisions that balance these key requirements. Now, in addition to these conflicting requirements, we also must navigate a large parameter space, as shown on the right-hand side of the slide. In order to define a battery cell, one must define the cell geometry, microstructure, and materials. So questions like what active materials will be selected for the anode, cathode, and electrolyte, what will be the size of the anode and cathode particles, and the volume fraction of the electrolyte, what will be the geometrical footprint of the battery cell, as well as the thickness of the anode cathode separator are all types of questions that we need to consider. And because cell design involves a larger parameter space with conflicting requirements, a trial and error process is not really the right method. Instead, we need to take a more systematic approach. Physics-based battery digital twins can greatly accelerate the design of a battery cell by connecting cell design to cell performance using physics-based principles. Now, the concept of these models is shown in the workflow depicted on the slide. On the left-hand side, we have the inputs, material properties, microstructural properties, and geometrical parameters. Some of these properties, specifically materials properties, require experimental parameterization. Those are then fed into physics-based electrochemical models that describe all the physical processes happening inside the battery cell. The models will generate as output not only the overall response of the cell, such as voltage, current, and state of charge, or SOC, but also the microstructural response inside the cell, such as local lithium concentration profiles, as well as local propensity for lithium metal plating, which can be detrimental to cell performance. Now, by using a physics-based digital twin, one can accelerate cell design and also reduce the number of required experiments. Today, I'm focusing on this cell development component of our overall battery digital twin that we have at Siemens DISW. But I want to let you know about this entire map. It's a solution that's connected, coherent, and reliable. And we offer a battery development solution that's a digital twin connecting processes all the way from battery pre-sizing and requirements determination stage through to battery management system or BMS development and integration. And within this accelerated battery development digital twin, we include tools and processes for characterizing your cell's performance, integration of that cell into a larger pack, and thermal and safety analysis, which we discussed in the last webinar, number 1, that we hosted a couple of weeks ago. Now, I can take that overall map and essentially flatten much of it out into these 6 steps, starting with material trade-off and cell design through to system integration. The battery engineering workflow also involves collaborations with other digital threads, so here and beyond here, that are enabled by a PLM backbone. And I'd like to also, well, I do use a lot of automotive reference during this talk. The workflow could be applied to any system, computers, battery-powered aircraft, lawnmowers, and many other applications. So let's start with the first step, which is material trade-off and cell design validation. This is where you may have a certain capacity requirement, weight, or material requirement, and we need to make sure our cell design meets these or at least gets close to them. You can explore the impact of materials and physical descriptions on your cell design. For example, you might be working with a lower energy density, but of course safer material for the anode. So you would need to make the cell size relatively large to meet capacity requirements. This material trade-off investigation is primarily done through 1D or lumped parameter modeling. So it's particularly fast, especially compared to a full-on 3D analysis. However, once you settle on a particular design or two, you can build those in our 3D physics-based model within SimCenter Star CCM+. In terms of the 1D modeling, we use Battery Design Studio here. This tool is really geared towards small chemistry changes, but large geometric changes of single battery cells. There are multiple types of battery cells that are supported, including spiral battery cells, stacked cells. This is an example of the layout. I'll show a demonstration later, but there are many different templates you can choose from to use within your design cell that you're building. And essentially, this tool is really built for a battery cell engineer. It has all these values that you should be familiar with if you're working with cell design, and it's relatively straightforward to run or to set up here with a highly resolved a set of documentation that comes with it. We also can generate bills of materials. So once you've built and designed your cell with all its materials and formulations for the electrolyte, active material, etc., you can kind of understand how much this battery might cost, if that's of interest to you. So not only is it, an engineering tool, but it can also help with kind of understanding the impact on the business from a financial perspective. Within Battery Design Studio, we include a physics-based model, so essentially plugging in the material properties and kinetics for the battery cell materials that you're using, and actually modeling the transfer of the lithium ion during discharge from anode to cathode, or vice versa during charge. And you kind of get an idea of all the resistances of all these different components of the battery cell. So we have the physics-based model, but also we have an empirical model. So you can take data, for example, from HPPC tests that you perform on a single cell, take that data, linear regress it to get the parameters for an equivalent circuit model. And then that equivalent circuit model can represent the entire battery cell, and you're able to run tests to understand the performance, understand even the temperature effect on temperature, etc. Now, you won't get granular, so to speak, details such as anodes, cathode potential. You'll only get the potential for the entire cell if you're using an equivalent circuit model. For physics-based models, you can get more granular information about the cell. In the 1D approach, now I'm purely talking about physics-based modeling from now on. In the 1D approach within Battery Design Studio, also called P2D, we consider that each layer and each location along the cell behaves identically. Hence, we're able to reduce the cell down to a one-dimensional system with only one electrode layer. This allows for rapid simulation on the order of seconds. So these are the kind of results that we can generate in Battery Design Studio. So this is a fast charge analysis at 25 degrees Celsius for one of our cells here. And we're looking at the voltage response here versus state of charge for different current rates. C divided by 2, 1C, and 2C, starting from 10% SOC. The goal is to get the cell here to charge from 10% to 80% within 30 minutes. And as a reminder, 1C is the rate corresponding to a full 0 to 100% SOC charge in 1 hour. 2C is twice as fast, so 30 minutes, and C by 2 is twice as slow, so 2 hours. Now, this model predicts that at 2C rate, over 55% of the SOC is accessible, as seen here, before the cell level voltage is reached, which is 4.2 volts. On the right, however, we show that this is not the whole story. The lithium plating limit is even more restrictive and is detrimental to safety and cycle life of the cell. If we consider the blue curve, which is the voltage at the anode separator interface, so now looking at the graph on the right, we can see that the voltage reached before the anode this voltage goes negative. The SOC reached before this voltage goes negative is 21% of SOC. In many cases, lithium plating is more restrictive than the full cell voltage limit, and this is why physics-based models are so critical, because one really needs to understand the internal physics of the battery cell in order to evaluate the true fast charge limit. Now, if we didn't have the physics-based model of the battery cell, we'd only see that it goes to 55%. So this is the whole cell voltage. So we'd be going well past the state of charge at which lithium plating may start to occur. This kind of information right here could not be obtained from equivalent circuit models and is not easily obtained from full cell experiments. And note that while we refer to the graph on the right as the anode voltage for simplicity, this quantity is more formally defined as the potential difference between the active particle and the electrolyte at the particle-electrolyte interface. Now, if this quantity falls below zero, lithium metal plating becomes thermodynamically possible at that interface. So if it falls below zero, likelihood of lithium plating. The correct equation right here for the definition of what we've described on the vertical axis is right here in this green box. I'd like to also note that much of this work was done by Aziz Abdullahi, who is a battery cell application specialist, cell design application specialist at Siemens DISW. Now here I show a fast charge capability map for the cell. The map displays the maximum state of charge, or SOC, the cell is able to reach versus the amount of charge time available. This map is constructed by evaluating the cell response to various C rates, as shown in the previous slide. It should be noted that the plot is curved because it gets harder and harder to get to higher SOC values. The red curve represents the charge map when only the full cell voltage limit is taken into account, and the blue curve represents the charge map where lithium metal plating is taken into account as an additional constraint, thus reducing the fast charge capability. And we observed that the initial design here is unable to meet the fast charge requirement, which I mentioned was going from 0 to 100% within 30 minutes. Here we only go from 10 to 66% SOC in 30 minutes. So we take the value of the blue curve if we include lithium plating. So we found that that initial design is unable to meet the fast charge requirement of going from 0 to 100% SOC within 30 minutes. And the question now becomes, what can we change in the cell design to improve fast charge capability? Now we have to assume that the material selection is fixed by the suppliers, and therefore we cannot change the particle size or the anode cathode chemistry. However, there are some tweaks that can be made to other cell design parameters such as electrode thickness, porosity, which is volume fraction of the electrolyte, and the anode to cathode ratio. Here we look at modifying the electrode thickness, which will decrease the length the lithium ions have to travel in the electrolyte. There is, however, a trade-off to this approach. Having a smaller thickness means that we need to have more layers to have the same total capacity. This, in turn, means that there will be more inactive material, like separators, current collectors, in proportion to the active material, which does result in a decrease in energy density. On the right, we show the result of the electrode thickness design exploration performed using Battery Design Studio. And we show the maximum SOC accessible at 30 minutes for 3 different variations. One at 86 micron layer thickness, one at 104 micron thickness, and one at 115 microns for the anode thickness. The 115 micron anode is the initial design, and the thickness of the cathode is changed in proportion, and the number of layers is also changed to keep the total capacity constant. We find that the fast charge target was improved from 66% to 71% when reducing the anode thickness to 86 microns, but there is a cost of about 3.5% in energy density. So reducing the layer thickness closes some of the fast charge gap, but not quite. And we now, we were targeting a specific energy density. We now fail that. We were targeting a higher value than what's now given based on this design. Therefore, in this instance, the electrode thickness design parameter won't solve all the problems, as it does reduce the energy density, but it can create opportunities for trade-offs. And like I said, there's no free lunch in battery cell design, as my colleague Aziz, who did most of this work, has often said. And trade-offs are common in the battery cell design industry. Now, in addition to changes in the cell design, fast charge limitations can be mitigated through thermal management. Now, most kinetic parameters increase with temperature, and on the left, we showcase the example of high temperature electrolyte conductivity in a typical electrolyte. The same principles apply to other kinetic parameters, such as the lithium diffusivity in the active particles, the exchange current density at the particle-electrolyte interface, etc. To obtain the charge map on the right, we surveyed the scientific literature to reasonably estimate our cell's kinetic parameters at 40 degrees Celsius. And based on this new map, which is the red curve, the cell can now be charged from 10 to 78% SOC versus the 66% SOC observed at room temperature. Now, additional preheating like this to 45 Celsius is expected to close the gap with the 80% SOC requirement completely. Again, we're trying to get to from 10 to 80% within 30 minutes. And preheating is therefore an additional tool to meet fast charging requirements. There's a trade-off, however, in the preheating requirement for energy from the battery, thus impacting the vehicle range. Now, preheating can also potentially accelerate calendar aging of the battery cells. It is to be noted that during the real-life fast charge, the battery cell temperature increases with time, resulting from the balance between self-heating rate and cooling rate. There's also a temperature gradient within the cell. Nevertheless, this simple isothermal example illustrates the general principle that a battery cell will charge faster if it is preheated. Now, I might have said in previous slides that we're trying to get to from 10 to 100% in 30 minutes, but it's actually from 10 to 80%. So just wanted to clarify. And in this case, we're at 78% SOC. Now, in cases where a cell designer would like to improve fast charge capabilities beyond cell design changes or thermal management strategy, one would have to revisit the materials and microstructure selection through collaboration with material suppliers, likely. But where do you start? Is the anode more at fault for insufficient fast charge capabilities, or the electrolyte, or the cathode? Physics-based electrochemical models can greatly assist in this effort by identifying the dominant sources of impedance in the cell. And physics-based models therefore provide the first step for an efficient and targeted materials optimization process. And here we're decomposing the cell impedance for a targeted materials optimization study. Now, in the 1D approach, we considered that each cell layer and each location along the cell behaves identically. Hence, we are able to reduce the cell down to a one-dimensional system with only one electrode layer. With a high-fidelity 3D model, also called P4D, we can capture layer-to-layer variations as well as spatial variations along the plane of a given layer. In this animation, we illustrate the cell response to an aggressive 25-second charge pulse at a current rate of 2C. At the beginning of the simulation, the cell is at about 50% SOC, and the cell is considered to be at a constant 25 Celsius temperature during the pulse. 2C is a high current that is above the fast charge capability of this battery cell, and this current is selected deliberately to highlight the phenomenon of lithium plating as well as inhomogeneous cell response. Now the video starts with an external view of the battery pack, after which we'll zoom into the pouch cell to highlight its geometry and meshing characteristics. We then display the lithium ion concentration in the anode and cathode across the section of a cell, and we observe a gradient of lithium ion concentration across the thickness of the electrode layers. We then isolate the anode of one particular layer and show the propagation of the lithium metal plating condition along with the surface of the anode over the course of the pulse. Let me go ahead and play that video again. See if I can go through that. So here we're getting to the cell, the geometry and mesh. Zooming in here, you can see the layer by layer lithium concentration in both the anode and the cathode. Here we're looking at the anode voltage. So negative anode voltage will correspond to propensity of lithium plating. Areas where we have a 1 here correspond to areas where lithium plating could occur, and 0 otherwise. We also observe inhomogeneity through the thickness of the electrode layer and along the layer plane, which you're unable to do in a 1D approach. Now, through this material and trade-off cell design validation study, we've calculated in general, through different studies rather, that cell designers can reduce testing by about 30% using our physics-based model of the battery cell. And you can also reduce the likelihood of a prototype failing during manufacturing. This is a demo of Battery Design Studio, so our 1D modeling tool for battery cell design. These are where those 1D results come from. You can edit the geometry parameters like the tab, height, width, etc. You have the active material here that you're defining for the cathode. There's a database of materials here that you can use. You can also define your own materials as well. You define the physical properties of the cathode here. You have to put in the equilibrium potential curve. There's some numerical settings that you have to write in as well. And you can actually run this on multiple cores to help you speed up the simulation. You can define a procedure here. So we're going to discharge with a current 5 amps, 1 amps, different procedures. Here 10 amps until the voltage is less than 2.8 volts. We can put all those procedures in a test and then execute the simulation where we're getting live results right here, or live simulation results. And it puts those results out in this output window live. Once we do the 1D design, we can then, and we find the best one at the 1D level, or one that we're happy with, we can go into the 3D model. Now this is built with a cell designer in mind. There are geometry parameters that you can write in that you should be familiar with as a cell designer. This is the mesh right here, very coarse, but you can also refine the mesh as well as what we're seeing here. It's using our directed mesher, conformal mesher in SimCenter Star CCM+. You have to input similar properties that you would for Battery Design Studio using the 1D modeling approach. You also have the equilibrium potential, voltage equilibrium curves, separator information, that you would have from your material database. This is the open circuit voltage versus absolute capacity. So all these parameters that you define can be viewed within SimCenter Star CCM+ quite easily. Now, in this case, I believe we're executing a duty cycle. So that's built through what we call simulation operations in Star CCM+. This is a template. And again, you can see you can get access to in-plane data through the thickness and across the surface of the cell data that you can't get in any 1D simulation. So electric current density here. So yeah, that is an example of a demo of the software interface both for Battery Design Studio and for the 3D cell design template within SimCenter Star CCM+. Now I've just shown a demonstration of the 1D modeling tool and how we can take that design and put it into our higher fidelity tool to build a 3D physics-based model to understand layer by layer variation in cell performance and even across the surface of the electrode. And you can look at localized lithium plating, for example, like I showed earlier. So we've developed a cell based on initial requirements, and we've also computed that data in a 1D using a 1D approach and also a 3D approach. I'd like to circle back to something, or not circle back rather, but focus on something here, which is the pack architecture definition. So this is something you might do even before you start doing like the material trade-off in cell design and cell performance. Essentially, this is a more systems level study where we can input in the context of an automotive vehicle, like you can put in the vehicle requirements like range, acceleration for top speed, and fast charging time. We can then get an output of pack requirements, including energy, voltage, maximum power. You can then estimate the number of cells required and make sure, like that earlier design that I showed meets these requirements. So this kind of study you would probably do before you actually start doing cell performance. You basically input the requirements for the car right here, and then you kind of get some information that you'll need for the batteries, such as energy density, maximum power, voltage, etc. Now, this is what that interface looks like. This is actually within SimCenter AimSim. So you define like things like your vehicle mass, the gear ratio, the tire width, the inertia drag. You simulate a driving condition to reach the expected performance. So you get some data here. Performance could be reached by a 48 kilowatt hour battery at 395 volts. That's what's determined here. And then you can begin pre-sizing the battery pack according to the derived specifications. So kind of understanding, if this battery, you can define a battery and see if it meets the requirements. There is a database in here within AimSim that you can leverage as well for the materials and compare different characteristics of different chemistries. So you can try those out. So this is kind of a way you can, understand basically what type of requirements you need for a battery pack. And then you can start designing the cell in a more detailed geometric manner in BDS, and then bring that cell into 3D in SimCenter Star CCM+. And to summarize, we used Battery Design Studio which uses a 1D approach to understand if we were meeting that fast charge requirement between 10 and 80% within 30 minutes. We made some adjustments to the number of layers of that battery cell, as well as the thickness. And then we were able to increase the amount of SOC that we were able to achieve, I think to 66%. Or something like that. And then we were able then to apply some preheating and get it to 78%. Although we did do that, there was, by changing the material number of layers, increasing that and changing the thickness, we did see a reduction in the energy density. So that was kind of a compromise we had to make in order to be able to do the fast charge. We then began to explore, this battery cell in more detail. using a 3D approach within our SimCenter Star CCM Plus template. And SimCenter Star CCM Plus is, of course, our multi-physics tool, a 3D multi-physics tool that we have at Siemens. And then I showed you at the end how we could kind of, even before you begin all these battery cell studies and cell performance and things like that we looked at in BDS and Star CCM Plus, you can actually use the SimCenter AIM-Sim, which is that 1D kind of network modeling tool, to pre-size the batteries pack. So you understand what are the requirements for the cell, and that's kind of the basis for your cell design. These right here are kind of our 4 SimCenter pillars. In the context of our accelerated battery workflow, how we can efficiently simulate multiple scales of the battery development process. Our integrated and streamlined workflows allow you to seamlessly make changes to parameters of both the geometric and boundary condition type. And all these processes can ultimately be supported by a PLM Team Center backbone. With that, I'd like to thank you for your time. We appreciate you being here. Sean and I both do. And yeah, that completes the portion of my presentation here. Thank you so much.
Thank you, John, for the presentation. And we now will have time to answer a few questions. Attendees, please keep typing your questions in the Q&A box on the left-hand side of your screen, and we will get to as many as that's possible. All right, Kevin and John, please turn on the Q&A.
Okay. John, here's one that came in during your presentation. The question is, you showed the physics-based model for a lithium-ion battery cell. What's the benefit of using a physics-based model compared to an empirical one?
Yeah, so I glossed over this in the presentation, but it is one of the main points we're trying to make with the study. Basically, with the empirical model, you get a full cell voltage. You can't get that granular information that you can with a physics-based model. With the physics-based model, we're actually able to look at what we call, I call it for simplicity, the anode voltage. And with that, you can get an indication of when lithium plating might occur, which lithium plating is this kind of detrimental process to the cell performance. So that's kind of one of the reasons, why we might use a physics-based approach.
Okay. The next question, what is a drawback of preheating the battery to increase the charge rate?
Yeah, so when you do preheat the battery, that energy to preheat it has to come from somewhere. So that comes from essentially the battery itself. So you do use a bit of the energy there, but it's worth it if you want to have charging in the right amount of time.
Okay. Question came in, can you explain more about optimization of battery structure development?
Yeah, so I mean, in this case, we modified the the thickness of the layers. So we decreased the thickness of the layers. So in the anode and the cathode, by decreasing that thickness, obviously the ions have to travel less distance so that we can have a faster charge. However, since we did decrease the thickness, we needed to maintain the same capacity. So we had to increase, we had to increase the number of layers, I believe. So you have to do things like this, but you have to make you can make changes to the battery cell, but you need to make sure that you are able to maintain the desired energy density or other requirements. And these are all parameters that can be changed within Battery Design Studio. These geometric changes like the thickness or the number of layers. You can even make chemical changes if you want to the materials.
Okay. This next question is for me. Are these sessions recorded and slides, can they be downloaded? I'll be sending the slides out tomorrow morning to all of the participants at this webinar, and then we'll send the recording soon after, probably next week. We just have to edit it and get it into YouTube. So check your email, likely first thing in the morning tomorrow and early next week, and you'll see the materials. And then another question for me, who can I direct my questions about battery simulation to? It's really the two people that you see on the screen right now, John Wilson with his email address and Sean Sullivan. And when I send out the battery presentation slides, I'll also include John and Sean's contact information. Great, so that's all the questions that we had. Lynn, I'll hand it back to you.
Awesome. Thank you so much for the presenting today and taking the time to answer the question that we have from the attendees. And especially for the attendee, thank you so much for joining us. And like Kevin said, you will receive an email with the slide, and also following that is the recording of this webinar. And with that, you feel free to sending any additional questions to Sean and John if you have any one more after today. And we would also like to encourage you to visit our website sw.siemens.com. There you will find more information about software and the solution that we offer. Okay, and finally, if you have any immediate project in mind, please give it a call directly. You will find the QR code in the webinar screen, and when you scan the code, you will see the list of the country phone number, so you can find the one for your location and give it a call to talk about your project or any question that you have about the solution. And with that, this concludes today's webinar. Thank you so much for attending and have a good one. Bye-bye.
Thank you. Bye.